Professor. So, Professor is Professor of Engineering at the University of California, San Diego. And he leads the Materials Virtual Lab at that institute. Now, one of the highlights, if any of you knows this Python Materials Genomics, this PyMatchGen. So Professor Ong is the founder and lead developer of it. He's also the principal investigator of the well-known Materials Project, which is an US Department of Energy initiative, which is also very well known. So Dr. Ong was also a recipient of the DOE and Early Career Research Program and the Office of Naval Research Young Investigator Program, and is also a private highly cited researcher in 2021 and 2022. So I would like to welcome Mr. Ong to the stage.
Good morning, everyone, and thank you for the kind introduction. It's definitely a great pleasure for me to be here in Portugal. This is actually only my second time in Portugal, so very happy to be here. Right? So today, what I'm going to tell you about is some of our research on universal graph deep learning models for materials design. So the focus here really is on what I call universal models, right? So models that are not customized for any specific chemistry or structure, but rather work universally across the periodic table and across many different structures. Okay, so I'm in the Department of Nanoengineering at UCSD. My group is called the Materials Virtual Lab, and we are a pure computational materials lab that focuses on high throughput DFT calculations as together with machine learning and AI to accelerate materials design. Okay. Now, I would like to start this. I always like to start this kind of talk by first defining what I mean by universal, right? So, I think many of you well know today we can use computers to design materials, and we have a very universal process for doing such computations, right? In fact, there's this very famous quote from Paul Dirac back in 1959. He said that basically the underlying physical laws for the mathematical theory for a large part of physics and the whole of chemistry are already known, okay? And this is already more than 90 years ago, right? And the difficulty is only that the exact application of these laws leads to equations that are far too complicated to be solved, right? And this is where really the advances over the past 8 or 9 decades have come in, right? So today, basically what we can do is that we can give a crystal structure, we solve the Schrödinger equation using some approximation, and we plug those equations into a computer, and basically what comes out are, after some analysis, are materials properties, right? And we can already do this for many different material properties. Okay, so for example, we can predict, we can estimate at least how likely a material is likely to be stable. We can calculate things like its diffusivity, its electronic structure, mechanical properties, and so on and so forth, right? So depending on your application of interest, there are many different properties that you can compute, right? So because we are using computers to solve the equations of physics here, what this means is that as long as computing advances occur, so in other words, as long as Moore's law keeps being true, our ability to compute material properties basically scale as Moore's law scales, right? So in the past, I would say 1 decade or so, what has happened is that there have been development of a lot of large databases of material properties. Okay, so the one that I've been involved in for the past 10 years or so is called the Materials Project. It is an open science project to basically make the properties of all known inorganic materials publicly available to researchers like yourself to accelerate materials innovation. Okay. So this was started under the former President Obama, and today if you go to the Materials Project website, which is materialsproject.org, you can see the statistics of the number of materials materials that we have. We have roughly about 150,000 materials computed with about 400,000 active users on a daily basis. Okay, so what I want to focus here is really on this graph on the right. This is too small. I'm going to blow it up a little bit, and this basically shows you a data history of the materials project. All right, so how many structures have we computed for each type of property, right? So you can see we started roughly in 2011, 2012 or so, and the initial years, the growth was a bit slow, but as the time goes by, we basically have computed more and more crystal structures. And as I mentioned, we already have about 150,000 structures and energies computed. The number of band structures is about half of that, and if we are talking about more difficult to compute properties such as elastic constants, we have about an order of magnitude fewer properties, right? So this graph highlights a few problems with just relying on a pure DFT, first principles approach to trying to explore materials, right? First of all, you notice that in the past 2 to 3 years, the number of materials that we have computed have stagnated, right? So we have been at about 140 to 150,000 materials for 2 to 3 years. So we have not been building, we have not increased the number of materials computed for quite some time. And the other problem is, of course, there are some properties that are just simply too expensive for you to want to do DFT or first principle calculations on all of them, right? And the problem is, of course, that this limits our ability to explore the space of potential materials, right? As you know, the space of potential materials is extremely large, right? So especially nowadays, people are looking at materials such as high entropy alloys, where you essentially have multiple elements that can sit on certain sites. And in many instances, you also want to model very complex systems like this polycrystalline model system, which is about 1 million atoms. So this is well beyond the ability for almost all epidential methods to compute. Okay. Now the good news is, of course, we now have at least a good amount of data. So with that good amount of data, we can actually start to do machine learning on the data that we already have, and hopefully we can then use those machine learning models to then predict the properties of more complex systems and explore spaces that we haven't explored efficiently, right? So let me first talk about what machine learning is. Okay, machine learning is basically the scientific study of algorithms and models that allow computers to perform a specific task without giving it explicit instructions, and instead what we are doing is recognizing patterns and inference, right? What we do is, of course, to give it lots and lots of data, and hopefully the algorithm learns the relationship between the input and output, okay? So I'm sure you have heard a lot about machine learning because there have been a lot of hype over machine learning applications for quite some time now, especially when we think about things like self-driving cars, or even just something simple like you go to Netflix and you look at your recommendation queue. All those are powered by machine learning algorithms, okay? Now, so how do we go about using machine learning in material science, right? So here I want to talk about how we can actually replace quantum chemistry, which is of course a universal approach that we use to predict material properties, with machine learning, right? And there are a few ways in which you can do that. Now, when we first started, when the community as a whole first started out using machine learning, we of course went for the most direct approach, right? So instead of going through all these steps in the middle, we decided to ask ourselves, well, can we just replace the entire infrastructure over here with machine learning, right? Can I hop from just the atomic coordinates directly to material properties? Okay, so this is the first approach in which you can use machine learning in material science, right? So the type of machine learning models that my group works extensively on are what are called graph neural networks, or they are also called message passing graphs. The reason why we are interested in graphs as a machine learning framework is because graphs are actually a universal representation for materials. Okay, so you can think about essentially the atoms as nodes in the graph and the bonds between them as edges in the graph. Okay, all these nodes and edges are basically represented by a vector of numbers. Okay, and what you do is that you then essentially pass information between the elements in the graph, right? So, for instance, you will update every single atomic information using the information from the bonds that are connected to that atom, and you then also update the bond information using the information from the atoms that are connected to it, and so on and so forth. Okay? So this representation is generic, right? You can use it for crystals, you can use it for molecules, you can use it for anything in between crystals and molecules. One unique feature about the type of graphs that we work with is this global state variable. Okay, so this global state feature actually allows us to introduce greater expressive power and flexibility in handling different data types and models. Okay, I'm going to show you how this is actually an extremely powerful concept, which I would say surprisingly a lot of graph neural networks out there do not incorporate it. Okay, so the type of model that we develop are what are called materials graph networks, or MAGNET. Okay, and by giving this architecture enough data, what we can do is that we can build models that directly predict certain properties of materials from the crystal structure themselves. Okay, so naturally, the first thing that we did was to basically go to the materials project. We look at all the different properties that are available in the materials project and try to build magnet models based on that data, right? So today we can predict the formation energy of a crystal structure to within about 28 milli-electron-volt per atom or so. Okay, we can predict the band gap of a material to within about 0.33 eV. We can also predict things like the bulk and shear modulus of a material, as well as doing a classification of whether a material is metal or insulator, right? Now, let me first answer a few questions. So first of all, giving you these numbers don't really help in the sense that you don't really know whether these are accurate enough for you to actually do materials design. I want to put this number in context, right? So there's actually this study that was done by my colleague Wenhao San back in 2016, where he basically looked at the energy above Hall for all the crystals in the inorganic crystal structure database. In other words, materials that are mostly have been synthesized by some experimentally somewhere. And what he found was that about 80 to 90% of the crystal structures actually fall within about 100 milli-electron-volt per atom above the convex hull, right? And with an accuracy of about 28 milli-electron-volt per atom, we are about one-third of the error, one-third of about 100 milli-electron-volt per atom. In other words, with this accuracy, we can already estimate pretty well whether a material is likely to be synthesizable or not. Okay, so this is quite a reasonable accuracy for this purpose, right? Now, I remember our previous speaker, Alessandro. He said basically the best model that we have in chemistry right now is the periodic table, and he wanted to know whether a machine learning model can actually learn the periodic table, right? I'm going to show you here that actually machine learning models do learn the periodic table of elements, right? So when we train our magnet models, what we can do is that we can extract the elemental embeddings, in other words, the vector that represents each type of atomic species, and we can calculate things like the correlation coefficient between those elemental embeddings, and we can also do what is called TSME projection of the elemental embeddings, right? Now, what you notice immediately from the correlation plot is that the correlation between elemental embeddings actually reproduce the periodic table, right? So in other words, things like the alkaline metals, which we all know are very chemically similar, they have very high correlation coefficients between the element and variance. Okay. Similarly, if you look at the TSNE plot, you can see that elements which are in the same group or same category in the periodic table, they actually are clustered together in this TSNE projection, right? For example, here you have the alkaline metals. Here you have basically the rare earths, okay? And all the rare earths tend to behave quite similarly chemically. And you then also have things like the alkaline earths over here in yellow, and as well as the main groups, okay? So, in other words, given enough data, machine learning models do learn the underlying chemistry of the periodic table, okay? And once we actually have this kind of learned chemistry, we can then exploit these chemistries to build models that are more data efficient and also extrapolate better to unseen chemical spaces, right? So let me first show you one way that we are using this, okay? So one of the things that we all know as material scientists is that high quality data is extremely expensive, right? So for example, if you are interested in the band gap of a material, for example, you are designing a solar cell, that's going to be one of the key parameters that you are going to look at. You can calculate it using the PBE functional, and that is relatively cheap in the context of first principle methods. However, it is also the most inaccurate, right? Today, if you just go to the materials project, you can already get, I would say, close to 60,000 PBE band gaps. However, if you want more accurate band gaps, you need to use other methods, right? Like, for example, the HSE functional, and there the data set size is much smaller, right? So we only have about we were able only to find a data set of about 6,000 HSE band gaps, right? And obviously, experimental band gaps are even harder to find, and we found a data set of about 2,700 experimental band gaps, right? So the way that we decided to solve this problem is, instead of trying to build one single machine learning model with each of these data sets in turn, which would be severely limiting because, for example, if you just have 2,700 band gaps, it is very, very hard to build a good quality, for example, graph neural network using this small data set, right? What if we can actually use the whole data set together to actually build one single model, right? So that's basically the approach that we have taken. We decided to use that global state variable to represent the fidelity of the band gap. So for example, we have one embedding representing PBE, one embedding representing HSE, and another embedding representing experimental band gaps. And what we can then do is that we can then use the entire data set to build one single model. So instead of having just 2,700 experimental band gaps in the model, we now have 60,000 TBE band gaps, 6,000 HSE band gaps, and the 2 to 3,000 experimental band gaps in one single model. Okay? Now, just to show you that it works, this is what happens. This is the error in the band gap if you build a model using each of these data sets in turn. So the TBE data set is the biggest, which is why the error in the band gap is also the smallest. Okay, so we can make very, very good predictions of very inaccurate PBE band gap data. Okay, so the error is about 0.3 EV or so. However, the error in the HSE and experimental band gaps are almost double that of what you get with PBE, right? Because the data set sizes are a lot smaller. So, however, if you build the multi-fidelity model that I just talked about, just by incorporating the PBE data as a low fidelity data set, you can actually get a 40 to 50% improvement in your predictions of the high value HSE and experimental band gap data. Okay? So in other words, we are essentially getting much better performance on the ML model just by relying on chemistry and structural latent features that was learned using the large PBE data set. Okay? Alright. Now, so as I mentioned, that was the first thing that the community actually learned to do. We started from structure and we immediately jumped to properties. However, this actually has a a few limitations, right? So the first limitation is that to construct the graph, I first need an input structure, right? And how do you actually get an input structure? 90% of the time you run a DFT calculation, right? A DFT relaxation. Now, this kind of defeats the purpose of a machine learning model, right? If you still have to use DFT to relax a crystal structure, how much time are you really saving, right? So the other more concerning limitation is actually that the fact that some material properties actually do not have a continuous or quasi-continuous relationship with structure and composition, right? So the reason why many people are interested in neural networks are, for example, is due to this what is called the universal approximation theorem, which basically says that a neural network with one hidden layer can already approximate any function for inputs within a specified range, right? Now, the problem is that most people read that theorem, they forget the requirement that the function itself must be continuous, right? And unfortunately, in material science, many times we deal with functions that are not really continuous, right? So this is an example of a very well-known lithium solid electrolyte material known as LLZO or the garnet, okay? Now people have studied this system extensively. They try to dope aluminum into this LLZO material and they measure its conductivity. And I want to point out that this y-axis is actually a log scale, okay? And what you notice is that just by changing the composition by very tiny amounts or the structure by a very small amount, you can already have a 2 orders of magnitude change in the ionic conductivity, right? So what this means is that if you are trying to build a machine learning model that predicts the ionic conductivity directly from the structure and composition, that model is very ill-behaved, okay? You are essentially jumping by 2 orders of magnitude in numbers with very, very tiny changes in your input, okay? So what is the better way? So a better way is to go for a smaller smaller step in your machine learning, right? So instead of jumping from structure to properties, what we can do is that we can use machine learning to model a smaller part of the process. So for instance, we can just bypass this solving of the Schrödinger equation, and we have what are called machine learning intelligent potentials that map things like the potential energy surface, which is the energy and forces on the atoms, to the atomic structure itself. And then we still rely on well-known physical laws, in other words, things like your equations of thermodynamics, kinetics, and mechanics, to actually derive material properties from the potential energy surface, okay? So machine learning intelligent potentials are basically, I would say, probably the most successful example of machine learning in material science today, okay? It is the most well established. There have been many success stories on machine learning intelligent potentials. They are rigorous and they work extremely well, okay? So the way that almost all the machine learning intelligent potentials work is you start with some description of the local environment around each atom. So the latest and greatest is what is called the atomic cluster expansion, which is developed by Rolf Dross in 2019. And you can actually show that the rest of the local environment descriptors are essentially special cases of the atomic cluster expansion, all right? And what you then have is basically a machine learning model that maps all these local environment fingerprints to the potential energy surface. In other words, what's the energy and forces of each atom based on the local environment fingerprint, okay? And people have used many different machine learning models, used anywhere from just simple linear regression all the way to your artificial neural networks to Gaussian processors, but by and large, they all work reasonably well, okay? So we actually did benchmark of all the big machine learning intelligent potential formalisms back in 2020, okay? So the darker the color, the lower the error, okay? And on the left, you basically have the energies, and on the right, you basically have the forces. And we actually benchmark all the different potentials across many, many different chemical systems. And what you can see immediately from this table is that the machine learning internal potentials definitely can achieve much lower energy and force errors compared to your traditional internal potentials such as your EAM and your embedded atom method and modified embedded atom method potentials. Okay? Now, this is already a big achievement, but for me, the biggest achievement of machine learning internal potential is actually not the accuracy and forces, right? But rather the fact that they are automatable, right? I can actually develop an automated workflow that can build me a machine learning internal potential for any chemistry that I'm interested in, okay? It used to be that developing internal potential is a black art, right? Someone will spend one entire PhD developing EAM for a BCC metal, right? Today I can build a potential, anyone in my group can develop a machine learning internal potential within a few weeks for any chemistry that we are interested in, okay? Now, just to show you what you can do with them, so for example, we have used machine learning internal potentials to study the lithium conductivity of solid electrolytes for all solid state batteries, okay? And previously, the way that people have studied the lithium conductivity of solid electrolytes is to use ab initio molecular dynamics. And the problem is that with ab initio molecular dynamics, you have certain limitations because of the cost of the ab initio method, right? So first of all, your simulation cell sizes tend to be small. You have to do high temperature simulations to get enough diffusion statistics. And then you have to do them at fairly short time scales, and then you extrapolate it down. And usually what happens with this kind of approximation is that you get predictions that are terrible, okay? So this is actually work from my group back in 2016, where we essentially used AIMD to predict the ionic conductivity of this material, LS7P3S11. We predicted an ionic conductivity of 57 millisiemens per centimeter. Experimentally, no one has ever seen a conductivity higher than 70 millisiemens per centimeter for this material, okay? So what it shows is basically that because of the cost of ab initio methods, you actually result in certain bad predictions, right? Now, later we actually use machine learning internal potentials to, we actually built machine learning internal potentials for 3 different chemical systems. And with machine learning internal potentials, we can actually build, do much longer simulations. We can do nanosecond time scale simulations of much bigger cells, so we usually go to a few thousand atoms at least, and we can go to very, very low temperatures. We can even simulate the ionic conductivity at room temperature, right? And these are the kind of results that we get, okay? And what we found was that basically almost all of the solid electrolytes, they have this transition at around 400 to 525 K, and because of this transition between different Arrhenius regime, your actual ionic conductivity at room temperature is actually much lower than what you would have gotten if you just extrapolate it down from room temperature, okay? And just to show you LS7P3S11, with this machine learning internal potential predict ionic conductivity of about 9 millisiemens per centimeter, which is very, very close to what the experiments actually get. And the reason why you actually have this transition in Arrhenius regime is really because of changes in the diffusion topology and dimensionality, okay? And in fact, this is also something that people have seen in experiments as well, okay? So this is experimental results for the this perovskite-based solid electrolyte, okay? All right, now in the final few minutes, I want to talk about how do we go beyond the current machine learning internal potentials. So first of all, there are several issues with them. Issue number 1 is all the machine learning internal potentials that are based on local environment descriptors, they actually scale as order n squared with the number of elements, okay? So what it simply means is that I can build machine learning internal potentials for systems with 3, 4, maybe even 5 elements, right? But if I want to go to something like, say, these 2 perovskites with about 7 to 8 elements, it is extremely difficult to fit local environment-based machine learning internal potential for this, right? My group actually attempted this a few years ago. It took us more than 100 active learning cycles, okay, before we can actually converge the potential. And the other thing is, of course, that each of the machine learning internal potentials, we actually have to custom fit them to each system and structure of interest, right? So this brings us to something that actually happened a few years back, which is there was this big advance from the Google DeepMind people where they essentially developed AlphaFold, which is for protein 3D structure prediction, right? So AlphaFold was such a big breakthrough that actually the two developers actually won the breakthrough prize back just last year. And when I saw this AlphaFold development, my immediate question was, why did they work on protein structure prediction, right? I mean, protein structure is one thing, but you can actually, what's more important is actually material structure. If you predict material structure, you can predict protein structure, right? So, inspired by that work, basically what we wanted to do was to see if our graph neural networks can actually be used to develop a chemically scalable machine learning interrupt potential architecture, right? So this is a modified architecture that we developed. So instead of just relying purely on message parsing graph neural networks, we also incorporate many body terms, in this case a three-body interaction terms within the graph neural network architecture itself. The reason for this is really to make it more efficient in terms of representing that local environment within the graph structure, okay? And using this M3GNet architecture, we can then fit machine learning interrupt potentials for any system of interest, right? So first of all, we show that basically, if you just give it the same training data as your other machine learning interrupt potential formalisms, you essentially get errors that are very similar, okay? No better and no worse than your, say, your neural network potential or your moment-tensor potential, and definitely much better than what you would get with your traditional interrupt potentials. But the difference is that because of the way the graph structure works, you basically just have a vector representing each element. We don't have the n-square scaling with chemistry that we have with the local environment-based descriptors, right? So to train an AlphaFold for materials, basically what we did was to basically go to the materials project. We look at all the DFT structural relaxations that we have done since 2012, and we threw in all the data into the M3GNet architecture to build what we call a universal interrupt potential, okay? So with that universal interrupt potential, we can actually now perform DFT-free structural relaxations and stability predictions. So we can show that we can get the energy of the ground state to within about 50 to 100 MeV per atom or so. Most of them are within 50 MeV per atom. Our structures are usually within 1 to 2% error of the actual ground state of the material, okay? Now, once we are able to make these predictions without DFT, we can actually construct the phase diagram and calculate the E above Hall. You can actually show that the distribution in stability is pretty similar to what you actually get with DFT. Okay? Now, of course, machine learning interrupt potential, other than just calculating things like energies and relaxations, you can also simulate a lot of properties, right? So for instance, you can calculate the phonon dispersion pattern and the phonon dot center, and this graph just shows you that essentially the phonon dot center that are predicted by this universal potential is actually in very, very good agreement with the DFT calculated ones. Similarly for the bulk modulus, and we can even calculate things like the ionic conductivity using MD simulations with the universal interrupt potential. Okay? Alright. Now, like all works in my group, we always publish our code open source. So if you are interested in trying out the potential for yourself, we have developed together with Intel this library called the Materials Graph Library. Okay, you just need to search for, go to matgl.ai, and you can already download all the models that we have fitted, and you can also develop new models for whatever application that you are interested in. Now, since this publication, there have been quite a number of companies who are very interested in integrating M3GNet into their software. So for example, there's the Amsterdam Northern Suite who have integrated the M3GNet potential into their software, as well as this company called Advanced Soft who actually helped develop LAMPS interface to the M3GNet potential. Okay. And obviously, because I'm the developer of PyMatGen, we also integrate that into PyMatGen. Okay. Just to show you how we are using this, we are trying to look for new lithium sulfide conductors for all solid-state batteries. These are the properties that we are interested in, and because we have a universal potential, we can now search through a much bigger space than before. We are looking at about 31 million crystal structures, and we can calculate things like the ion conductivity as well as the electrochemical stability, and we can actually identify regions where we actually are likely to find good lithium sulfide conductors. You can see that a lot of the well-known lithium sulfide conductors sit within this region. However, there are also a lot of materials that people have not explored, and we are actually looking at a lot of those materials more closely. Okay? All right, I'm going to skip this. I just want to conclude by saying that, well, using graph representations, we can actually build universal machine learning models for material science. The MCGNet architecture is quite robust. We have actually tested it on a lot of different data sets now. Now, really, we are constrained by DFT training data. And finally, universal machine learning models such as MCGNet, I would consider them like the foundation models for material science. You can use them for many, many different applications, both for dynamic and simulations of materials as well as design of materials. You can also start from them and then build a custom potential for the application that you're interested in. Okay. Now, this is my final slide. Basically, what we are doing right now is really to address some of the bottlenecks in building universal internet potentials. First of all, is obviously data. We are working together with the materials project on what we call the MatPass dataset, which is the materials potential energy surface dataset. We are going to make this publicly available. It will not just be 0K DFT structural relaxations, but also finite temperature MD simulations. We will have TDE as well as R2 scan data. We have built models that have more physics. We have incorporated charges and magnetism into the MCGNet architecture. And one thing that we also would like to see happen is really people developing better software, right? So one of the issues with most of the machine learning internal potentials is that they are much more costly than your traditional internal potentials such as EAM and MEAM. So what we really want to do is to basically have much better scaling for those potentials, as well as better integration with some of the materials modeling software such as labs and ESC. Okay. So I just would like to acknowledge funding from the Department of Energy for all this work. If you are interested in looking at the paper, this is the paper on the universal graph potential. And of course, everything is on our GitHub repo. I invite you to check it out, and I'm happy to take any questions.
Thank you, Professor Ang. So the floor is now open for questions. Quickly.
Thank you very much, Chico. Very nice presentation. So I have I would say, a kind of general question regarding materials project database.
Mm-hmm.
It's two questions and one question. How many virtual materials studied with DFT and so on were synthesized, were successfully synthesized in the lab? And how many of those found practical value in different domains of applications, batteries, whatever?
Yeah.
Maybe percentage, right? I would like to know how many materials were successfully synthesized in the lab in percentage, and how many of those found a practical value. That means that they are really advancing, technology in practice, right? And they are just not incremental, I would say. Thank you.
Yeah. So I would say the percentage that are synthesized is actually not that bad. So most of the time, once we actually have done all the screening and filtering, by the end, when we ask our experimental colleagues to go and synthesize it, we hopefully already have a relatively high confidence that the material might be synthesizable. Now, that said, of course, we don't take into account every single metric of synthesizability. So I would say probably around 25% or so you can synthesize. Sometimes not phase pure, sometimes phase pure, but synthesizability is more doable. Now, as for practical value, that's where it's tricky. So I would say, if you are saying, will the material have the properties that we predict? Most of the time, yes. But the problem usually comes from there are so many metrics that you have to satisfy for actual commercial application. And also, so I would say probably not many have been actually commercialized right now. So that percentage is much, much lower.
Thank you.
For sure.
We have time for more questions from the floor. We have. Yeah, please.
Great. Lovely talk.
Thank you.
I know that we have many researchers that are interested in applying these types of foundational models for material science in the audience today. And so I was hoping that for their benefit, you might compare and contrast the different foundational models for materials that are in the literature now. What do you think are the unique strengths or perhaps weaknesses of M3GNet versus other ones,
Yep.
ACE and et cetera?
Yep. Great question. So I would say that in terms of architecture, there really isn't that much differences, right? So they are all based on message partitioning neural networks with some description of the local environment. Some of them are equivalent, some of them are invariant. But by and large, based on our own benchmarking, the differences are small. So I would say you will want to choose the model that makes the most sense for you in terms of coverage of chemistry, as well as ease of use, right? And I think in my group, we try to make every effort to make sure that our models are out there and easy to use for most people. So the first model, the M3GNet model, the data set is much smaller than the newer models because they actually use the entire data set. But as I mentioned, we are developing this MapPass data set, which will be much more comprehensive than what was used before. And what we are going to do when we actually have the data set is we are going to fit every single model using this one. So you will have access to a much better model across all the chemistries. Now, one thing that we have noticed is that it is a bit surprising, the different models, some of them may have technically lower energy and force errors, but it turns out that they are much less stable. So there is some inherent trade-off between how low your energy and force errors are versus the stability of the calculations. So yeah, so that would be my rule of thumb. I honestly don't think that there is some like a gigantic difference between, say, Maze versus M3GNet in terms of actual architecture and errors. So, yeah, I think there was one more.
Yeah, so I'm curious about the transferability of these universal potentials, because you mentioned magnetism. That's, from my background, a big question when it comes with the effects on the lattice. But also stuff like, for example, disorder. For example, the atomic environment of a solid system that's ordered will be very different from something like a high entropy alloy, for example. Do you see it as being applicable also to these systems, or is it something that you need to create a data set to address it specifically?
Yeah, so definitely the potentials generally work as well as they can within the domain of the training data. I mean, that's not surprising. And in the materials project, it's mostly all the crystals, all the inorganic crystals, right? So if you are hypothetically interested in using this potential for organics or proteins or any sort of those kind of thing, I would probably say the performance, I wouldn't expect them to be great. Or if you are trying to simulate things like surfaces, again, I think I wouldn't expect the performance to be great, right? However, insofar as your local environment is represented within the data set, I would expect the performance to be decent. So for instance, when we talk about high entropy alloys, as long as the local environment that you see in your high entropy alloy, like for example BCC coordinated atoms or FCC coordinated metal atoms, and if those are represented within the data set, the potential should work reasonably well. And that's what we have found. So even when we model a system that technically is not in the materials project, but the local environments have been seen in the materials project, they are actually okay. Now, regardless, even if, let's say, you found a system that the universal potential doesn't work really quite as well as you would like it to be, starting from the universal potential and giving it more training data to fine-tune it is going to be a lot more efficient than starting from scratch and building a machine learning intelligent potential on yours by yourself. So yeah, that's the general answer I have for you. Yeah.
Okay, we have time for one more quick question before we move to the next speaker. No questions? So I'll ask a quick question. So streamlining so the process of contributing to these databases is surely important to get more data. Is the human factor still at play here? So can someone that wants to contribute still make a mistake, and that mistake has to be identified? How is it identified?
Yeah, so in Material Project, we have something called the MP Contribs framework, where people can actually upload data to Materials Project, and we will host the data for you and present it in a nice interface, and other people can then download it for use. And there will be acknowledgement that this data came from, for example, you, and to cite, if you are using this data, they should cite your work. I think, obviously, as with any large data set, error checking by hand is impossible. So, but what we have found was that actually it's also easier to detect errors in large data set, because you will always identify something inconsistent, right? So you find that, okay, I don't expect this material to have this property, right? And you will check it, and there's also some degree of uncertainty quantification, right? So if, let's say, you have multiple different models making predictions on one particular model, one particular material, and the three models agree on the prediction versus the three models have wildly different predictions, those actually will be an indication of how reliable that prediction itself is. So, yeah.
So you have some sort of procedure to identify these outliers.
Yes, there is an automated process. It's not 100%, but it helps with some very obvious errors, of course.
Okay.
Yeah.
Thank you. Let's thank Professor Ong again.